So this chapter dives into wind, the phenomenon of wind, and wind is basically air that wants to move, air that wants to go from point A to point B. And why does air want to move? We're going to get into the crux of that, but we need to revisit air pressure. And air will want to move from a high pressure to a low pressure, and as it does so, it creates what we call wind. So it's important to understand pressures, and we're going to start talking about that in a minute. But this slide just kind of looks at kind of a couple different things wind does for us. Wind can power our sailboats. I've never gone sailing, but it looks like fun. Wind can also be have a devastating effect on objects that it basically pounds against. Okay. So when we talk about air pressure, remember what we're talking about is these basically air particles, and if you look around the room, wherever you are, most of these air particles are nitrogen gas, some oxygen gas, and a variable amount of H2O gas, all right? And they are pounding in all directions. Gas particles have a lot of kinetic energy. So when you think of air pressure, kind of think of those little gas particles hitting things. And one of the things we've already talked about, go ahead and erase this, is that, and we're going to revisit it again here in this chapter, is that with regard to pressure, because I talked about pressure is important in creating wind, if this is the Earth's surface, as you go up in elevation, the air gets more sparse or less dense. So here we go. These are my gas particles here. Okay, it gets more and more sparse. Okay, so actually the more dense air at the bottom, vertically speaking, now this is a kind of a vertical look at our air density. We have, generally speaking, we have a high pressure down here near the Earth's surface and a low pressure up here. We'll talk more about this. This is called the vertical pressure gradient, or vertical pressure change. Gradient and change can be used interchangeably. So the more dense the gas, the greater the pressure. And I don't have a whole lot to add to that. Now, as we are walking around here, so I'd kind of draw your attention to, I'll put a stick figure here. Somebody's walking on the surface of the Earth. In general, those gas particles, most of them are nitrogen, some oxygen, a variable amount of carbon dioxide and water. They are banging on all of us at 14.7 psi. PSI stands for units of pounds per square inch. Pounds per square inch. Now, in meteorology, we don't really talk about air pressure or gas pressure in PSIs, pounds per square inch. We use a few other units. On a weather map, and we're going to be looking at a few of them here in a minute, they draw surface pressures in terms of millibars. Milli is the prefix 1/1000th of, and actually bar is a unit of pressure. So this is on maps. We do millibars. Now, if you're doing your weather log, there's a good chance that if you've been checking the internet, they will talk about pressure in terms of inches. And actually what they don't say is it's inches of mercury, and I'll tell you why it's actually inches of mercury. In physical science, a lot of times we talk about units of pressure in terms of atmospheres. Now, in terms of the 14.7 psi, pounds per square inch, we are feeling right now, in general, now we're going to see that varies from day to day, and it varies from location to location, but just in general, sea level pressure is 14.7 pounds per square inch. That's equivalent to 1013.25 millibars. It's equivalent to 29.92 inches of mercury, and it's equivalent to 1.00 atmospheres. So let's take a look at today's pressure. Let's see if the internet will work for us. And I think this is going to take us to the pressure at Keokuk, or the weather conditions at Keokuk. Yes, it is. So let's see. Now I have a slide coming up here, I think, in a minute, and anytime somebody talks about atmospheric pressure, that's the same thing as barometric pressure, and that's the same thing. By the reason atmospheric pressure is sometimes called barometric pressure is because we use a barometer to measure it. And so it's the same thing. So let's see, down here, where to go? There it goes. It just simply says pressure. And actually right now, the inches of mercury is 30.2 inches of mercury. I don't know if you can see it very well, but what we call the tendency, and we'll be talking more about this, is it has an up arrow. And so we say the tendency of the pressure is rising. Okay, so 30.12 inches of mercury and rising. Okay, so inches, whenever they say inches, they're really talking about inches of mercury. So I'm going to kind of show you, relatively speaking, comparing inches of mercury with millibars. So millibars is when we look at our weather maps, we call mixed weather maps, surface maps. There'll be these lines, these contour lines for pressure, and those will be in units of millibars or MBs. So just kind of some significance here. First off, what did we say? I forgot already. What was that? Today's pressure in inches of mercury in Keokuk was what, 30.1 or something like that? Okay, so that's kind of where we are today. Now, one of the things you might notice, this is striking to me, I think, is that in terms of inches of mercury, I mean, it doesn't have to change very much inches of mercury, and we've got drastic changes. Now, over here on the right, I'm going to tell you what I mean by drastic changes. The highest sea level pressure ever recorded was 31.89. I mean, do you see what I'm saying? 30.1 versus 31.89. That's not very many difference in inches of mercury, but it's a big difference in pressure. The highest recorded sea level pressure in the U.S. was 31.42 inches. We're going to talk about anticyclones coming up, but a strong anticyclone system would have a central high pressure, this would be an H on your weather map, of 30.71 inches of mercury. I mean, and one of the things when we talk about anticyclones, they sound exciting, but they are boring. They can have really kind of interesting consequences, but they definitely don't bring our severe weather in general that we think of. All right, so and I think you saw this number before in terms of kind of sea level, that 14.7 psi. We are running about 29.92 inches of mercury, or 1,013.25 millibars of pressure. So those are all, these first three are highs, relatively high pressure, and this one's kind of normal. Now let's look at low pressures. Kind of the antithesis of an anticyclone is a cyclone. And these on the weather map are going to be L's. I'll just kind of give you a precursor. And if we kind of have a nice, strong low pressure, what you're talking about in terms of inches of mercury would be, in general, like 28.94 inches of mercury. Now, our low pressures bring our severe weather. Now, we're going to see later on that anticyclones or high pressures can bring severe weather. But in general, when we talk about thunderstorms and that sort of thing, we think of our central low pressure system. So notice that hurricanes, and to a lesser extent, because they're so fast and all that, but tornadoes too. But hurricanes, one of the ways that they're gauged by how severe, what sort of damage or intensity they have, is with regard to their pressure. And actually they have a really low, very low central pressure. So 26.71 inches of mercury will scare, well, meteorologists as far as the intensity of a hurricane. Lowest pressure ever recorded in the Atlantic Ocean, or for an Atlantic hurricane, was about 25.99 inches of mercury. Lowest ever recorded sea level pressure was during a typhoon. Now we're going to talk about typhoons later, but actually typhoons are a different part of the world. They're equal to our hurricanes. The generic word for hurricane and typhoon are tropical cyclones. So how do we measure the atmospheric pressure? Well, I mentioned that atmospheric pressure and barometric pressure are the same thing, and that's because the device we use to measure pressure is a barometer. Here we go. Barometric pressure, air pressure, and atmospheric pressure are all synonyms. So I'm going to talk about two barometers. I'm going to talk about the Mercury Barometer and the Aneroid Barometer. And actually, you might have an Aneroid Barometer at home. I doubt if you have a Mercury Barometer. Mercury Barometer. Some of you probably already know that Mercury is one of the, I'm going to say, two elements that at the Earth's typical temperature and pressure is a liquid. So actually, the way a Mercury Barometer works is you have to have liquid mercury in a pan. Now this pan is rigid. I know it looks silvery like the whole thing is mercury, but actually it's got in a container, and we have liquid mercury in the container. And so what happens is we said that, these are my gas particles. We said that the gas particles, nitrogen, oxygen, carbon dioxide, water vapor, are banging, if it's a gas, has a lot of kinetic energy, banging in all directions. Okay, so we said that, in fact, we even put a, about 14.7 pounds per square inch is the amount of banging, excuse me, that the gas particles in the atmosphere would do about sea level. So what happens is it gives a certain amount of bang to the liquid, now this is open right here, to the liquid mercury, okay? And then consequently, however much banging in this direction it gives to this liquid mercury, then actually has a consequence for making the liquid of the column of liquid mercury move up. So as you increase the pressure, what's going to happen is your liquid mercury in this column will go up. Now the way this was prepared is, this is a closed tube, and it was prepared with a vacuum and then inverted, and there's an open end. Down here is an open end of the glass tube, and the mercury slides up that. So when somebody says, for instance, it's 29.92 inches of mercury is the barometric pressure, what they're doing is they're literally measuring this distance that mercury has climbed up the column, the glass tube. All right, there you go. Well, I said you probably don't have a Mercury Barometer, but you might have an Aneroid Barometer. And the way the Aneroid Barometer works is that it's usually kind of a pretty brass color, and the little box, this little box right here, actually as pressure hits it, it will squeeze, and as it squeezes, it will make this little, I don't know if you can see this spring, but it'll make that little spring move, and as that spring moves, this black dial will show a decrease in pressure or an increase in pressure. See? I don't know, that's pretty cool. So there is, oh, let's see, what else do I want to say? Now, the black needle moves relative to the amount of squeezing or flexing that that box is feeling because of the atmospheric pressure. So the black dial moves. Now, this gold dial can be set by you. We set this. And the reason we set this, and they'll give you instructions if you buy an Aneroid Barometer, but what you do is you set it, and then 24 hours you come back and look at it and look for tendency. For instance, we can see the tendency here. If this was set maybe 24 hours ago, can you see the tendency here is for the pressure to be increasing? Okay? And if the pressure is high, we have relatively, if we are under the influence of a high pressure, remember I said high pressure is boring, we should have kind of clear skies. If we have low pressure, we can generally expect some sort of cloud cover or even storms. So if the pressure is rising, we'll have clearing weather. And like I said, I can tell the way this is that if we were looking for tendency by setting our dial here, looking for tendency, we can see that the pressure is rising, so skies are clearing. Now, if we were to see the opposite tendency where the pressure was falling, we would expect some sort of precipitation to be coming our way.